Nadia and Graham, the floor is yours.
Hi, I'm Nadia from FactWorks from the Berlin office.
Hi, and I'm Graham from Dynata in the London office. So welcome to the presentation, The Death of Classical Monadic Designs, a self-learning algorithm for concept testing webinar. First time I've ever said that. And thank you for taking the time to listen live to this webinar, or if you're downloading it at some point in the future, good afternoon, good evening, and hope you had a nice Christmas. With this in mind, good to have so many people virtually on this webinar for this session. Hopefully this is an indication of how interesting the topic of machine learning and automation is and its application in insight. So with this in mind, I'd like to take a closer look at how self-learning algorithms can produce better results for naming and concept testing. It is true to say that for new product developments and for brand management, name and concept testings are the indispensable part of the process. And when testing brands, names, and contents, the gold standard for producing solid results are through using a monadic methodology. That is, as we know, serving only one name or concept per respondent to select the best. Monadic testing seeks to get as close to reality as it can be in a market research survey. Monadic testing is a tried and tested solution, and over the years has evolved from a face-to-face methodology, those are the days, to an online solution as it is today. Although with its advantages, monadic testing also comes with a number of drawbacks. It usually needs a lot of sample for each concept or name to give a robust findings, and particularly where the client wants to test many concepts or names, and this obviously can take time. Monadic testing can struggle with difficult to get hold of respondent types, and with very targeting consumer groups, it may not even be feasible. Finally, monadic testing means that there's still the same number of sample sizes per concept committed to get and we still commit ourselves to get a full sample from choosing the one we want, which is very inefficient, wasteful, and expensive. So is there a way to make the process more efficient? Concept testing be designed more intelligently? Well, we think there is, by using machine learning and smart algorithms to satisfy the twin needs of high quality concept testing while making the best use of time and resources. I can't claim to come up with the idea, and that's mainly down to Nadia and her team at FactWorks, but with Dynata's help, we've developed a solution. As you can see from the screen, the monadic testing has sets up in number of concepts, and we don't know before we start what the performance of each concept is going to be. I mean, we have our own gut feeling, but from our clients want objectively to know which one is the best and go through the process. The clever thing with the intelligent algorithm developed by FactWorks turns this traditional monadic design into an adaptive approach. Ta-da! With careful sampling, this adaptive approach automatically learns which concept is well received and which is less so. The algorithm then decides for itself which concepts are assigned more respondents and those that get fewer. So far, so theoretical. How do we prove that it works? By going head to head, the classic monadic design versus the adaptive design. So in this case, we validated this using an online survey in Germany and the UK with respondents from the Dynata panel. A simple A/B test, monadic design versus intelligent algorithm, was carried out. We decided to test a name for a shiny new app. We looked at 5 names, all fictitious but credible for a new knowledge app, similar to Netflix Explain, sort of thing that explains new stuff and gives short tutorials on how things work, like blockchains, etc. And the concept was explained on screen with the names tested, the ones you can see here on the right. And they were called, did you know, Apredo, and so forth. So looking specifically at the UK, we asked 20 questions regarding the name and conducted online fieldwork during September 2018 with a representative sample of adults aged 18 to 65, 1,500 respondents for the monadic test and 1,500 for the adaptive test. And the sample was matching samples all the way through the survey, so we ended up having a steady flow. So there was no decision made until a significant number of sample was done. I should say, the implementation of the algorithm was made technically possible with the help of Decipher, who are good at this sort of stuff. So we thank their help. So that's the practical description of how we tested the approach. And so what does the algorithm actually do and how does it work? Well, Nadia has the answers and I'll hand over to her now.
Thanks, Graham. So let's take a closer look at the algorithm. And our self-learning algorithm actually builds upon principles of an existing one. You may know it as Bayesian Bandit or multi-armed bandit algorithm. It's not to be confused with Bayesian networks. That's something different, but it actually shares the same underlying Bayesian statistics principles. So how to explain it best? Well, imagine a night in Las Vegas. You decided to gamble a bit and find yourself before slot machines or one-armed bandits. What is it that you're probably going to do? And for argument's sake, let's assume that not every machine has the same expected payoff, but that there are differences in payoff. So you could invest in several ways in several one-armed bandits. You want to maximize rewards, obviously, so you would want to pick the one with the highest payoff. The problem is that you do not know which one it is from the onset. So you would spend a little bit across several machines and see which one has the highest return, and then more heavily invest in that promising one going forward. Still, it could be that that is not the best strategy over a longer period of time because things could change. So you would put more money in the most promising bandit, but you would also put a little one in others from time to time just to check if others outperform the chosen one over time. So you would be dynamically adapting. And that is exactly what the algorithm we looked at does, which is the statistical best approach balancing safety and profit. And where can we find examples of this Bayesian Bandit algorithm? Where does it apply? Well, nature would be one, evolution. How can creatures find the best survival strategy? What behavioral strategies develop over time? Who do they compete against and who better not? We can also find it in website optimization and conversion when testing different designs based on click rates, for instance, or ad testing and adapting on the fly and showing the more promising design. And the algorithm is partly applied in clinical studies where you have different options for treatment. And with no hypothesis in the beginning, would adjust probability of being assigned to treatment group based on results during the testing to take the most promising therapy with more patients for solid results, but still would want to continuously check what the most promising option is. It's not widely used in market research yet, so we took a shot and applied it to concept and name testing. So what we see here is simulated results for this existing Bayesian Bandit algorithm and our market research use case. And the simulation shows that the Bayesian Bandit works. The winner concept is identified by the algorithm and more sample is allocated to the winner concept. But what we also see here is that the algorithm is kind of greedy and that it learns too quickly. There is not sufficient information for the other concepts. But in reality, we as market researchers or research buyers, we know that the final pick might not be the one winner concept identified in research. There could be legal reasons, other reasons why it might make it necessary to have a good read on the second and even third best alternatives. So we tweaked the algorithm and built upon these principles of the Bayesian Bandit, but we optimized for our market research purposes and created our own algorithm out of it. And one thing that we did here is that we established a starting sample size to be achieved before the algorithm starts to learn and before it does his magic. And that is, for example, that it has a few observations per concept to have a baseline understanding per concept to start with. And then we defined that the algorithm should work within a lower and upper limit of observations, so that there's at least 50 observations per concept here and a max of 600. And when the algorithm learned that concept X, for example, is significantly worse compared to others, it would not be shown, but would still be shown if the minimum sample size is not reached, so would be occasionally be repeated to make sure that the minimum target is achieved. Again, this is simulated data. So what do we get with the real world survey data that we have? From the study we did together with Dynata, the first thing we found is that we indeed get more information about top concepts, and in our examples about the top 2 names. 2 main findings here. First, the winner is identified, and also the next best one with more sample than we would have obtained with monadic design here. So more cases to analyze, and thus more diagnostics. Right, we have, for monadic would have been 300, so here we have more for the top 2 names. There's more from adaptive to analyze and to get, where we're not wasting sample on less promising options that underperform. And the second observation is that we still get sufficient data points for a baseline information on those less promising names. So it's not that we don't have any info, we just have a baseline understanding, which is what we want in reality. So for Noli here, for example, the least promising name, we would still have 50 observations and completes for an overall read. So what does it highlight here? It highlights a bit that the algorithm allows us to cover more names and more concepts, for example, because we have the focus on more promising names with a baseline understanding on less promising ones. And what other benefit is there in knowing more for top concepts or names? Well, firstly, it means we have more diagnostics, for example, open-ended follow-up questions on associations or likes and dislikes that we have more and can more analyze. Secondly, it also means we have the possibility for data cuts into subgroups, and that we have thus more, and then we can detect more easily differences for specific groups. On this slide, we can visually see that with the red areas here, indicating that sample is small or limited, and that is more the case within monadic design. We have more red areas here, meaning limited sample availability. So certain data cuts by age and gender are limited in monadic, but possible in the adaptive design, for in this case, the 2 top names. But also when looking at the blue areas, like the device split here, for example, and looking at desktop specifically, we see that we have something like 150 with adaptive, but only about 70 completes with a monadic design. So we can still dive a bit deeper into desktop further with the adaptive design here, more easily with a more robust base. Well, if you now say, I'm only interested in speed, that's the other side of the coin, and the other area where the algorithm can be more efficient. For the top 2 winners from our study here, Watch to Learn and Did You Know, monadic would have stopped after 1,500 observations overall, right? That would be field. With the adaptive design, we could have stopped the field after 999 interviews already, because the top 2 names would have been filled with up to 300 observations each already then. So this approach can save about 10 to 20%, maybe a bit more sample, speeding up the field time, which is essential. And that depends a bit on characteristics of the study, of the number of concepts you want to test, but something around 20% is a fair assumption. And it makes the survey also feasible, and not only speed, but also is a question of feasibility, because think of hard to reach target groups in B2B or other narrow target groups where sample availability might be limited. The algorithm increases efficiency and feasibility here. So we found these exciting results with the data, with the real world data. What we also wanted to check and validate in our research was that the profile of respondents wasn't too different. And this is something that you can see here. Indeed, for the top name here, which is Watch to Learn, looking at the profiles of survey participants in both monadic and adaptive design, it becomes clear that they match quite well. Small differences are here in gender and smartphone usage, but overall a consistent picture with hardly any differences. So that's good news here. So our adaptive algorithm indicates that it offers potential to boost efficiency compared to currently employed classical monadic studies. Maybe doesn't mean the end of death of classical monadic designs, but it's for sure something like a next level efficiency in monadic testing. main benefits of the self-learning algorithm includes more information for more promising concepts, which we are most interested in reality anyway. More flexibility due to being able to cover more concepts, more names. Could also be items that work here. So beyond the concept test, there's flexibility as well. And on the other route, it can lead to time savings and efficiency with reaching the goal faster. It can make studies feasible, even with hard-to-reach target groups. And it's not limited to our study here, can be adapted for future specific use cases for your research. So, Graham and I would like to thank you very much for your attention. Feel free to reach out and to ask questions, talk to us. And now handing over to Ray.